I will later go for study.
So I know that in the past I have done kind of a list of topics, but I've kind of already done that with highlighting and bolding in the resource guide. So instead of spending time on that, I have actually come up with a set of practice problems for us to do that will help stretch the muscles we will need for tomorrow. Okay, so it's like a whole exam. I have all of these questions for us to do. And most of them are pulled from like homeworks or like concepts pulled from homeworks, either from this year or from last year. Are there any general questions before I start going through this? Cool. Okay, so first question I have for y'all. You have 2 starting materials and 3 products. And we have 2 NMRs here, which I guess it's kind of hard to show them at the same time as the compounds. Would you rather I give you time to try them on your own or just work through them? Little bit of time? Okay. I'm gonna try and zoom out so that you can see all the necessary information. So there's 2 NMRs, one corresponds with 3 and one corresponds with 4. It is up to you to figure out which corresponds with which and then label those signals. Once you guys write down the structures, if you give me a thumbs up, I can zoom into the NMRs. Okay. Nice. Okay. This is a way that you can see the structures and the NMRs. So these have the NMRs and this one has the structures. Are we ready for me to start talking through it? Can I get thumbs up of, yes, I'm ready, give me a few minutes, give me a lot of minutes? Okay, I'll give you a few more minutes. Yes. I put it on Canvas. Okay, are we ready to start covering NMR? Yes, no, maybe so? Yes, okay. Do I have any confident souls who would like to come up and try their luck up here? Or at least start walking through? Do you want to pick a spectra or a compound?
Okay, so, oh, this is loud. So first we're gonna circle the proton group. So 1, 2, 3, 4, 5. So that's identifying. So we'll just label them A, B, C, D, and E. Sorry, my handwriting's really bad. And then you're gonna find the intensity. So how many hydrogens they have. So A has 3, B has 1, C has 3, D has 2, and E has 3. After that, you're going to find the multiplicities. So that is n plus 1, or as Jess normally does it, the neighbor method. Can I scroll down? Is that okay? So multiplicity. So A is this. So n plus 2, so you're going to look at the carbon next to it. There is no hydrogen, so it's n plus 2, so 0 plus 1 is equal to 1. B, neither carbon next to, of the 3 carbons next to it, one of them has 3, so it's going to be 3 plus 1, which is equal to 4. C has 1 carbon that has hydrogen, so it's 1 plus 1, 2. D's carbon next to it has 3, so 3 plus 1 is equal to 4, and then E carbon next to it has, carbon next to it has 2, so it's 2 plus 1, 3. So those are going to be your multiplicities. So that's how many peaks your thing has. So it's A is 3 and has a multiplicity of 1, so this is going to be A. B has a multiplicity of, sorry, not multiplicity, that's intensity of 1. 4 peaks, this is going to be B. C has an intensity of 3 with 2 peaks, so it's going to be this one. D has an intensity of 2, 4 peaks, it is going to be this one, and E has this one.
She's correct. Do people have questions about that? Or the method that she used? Yeah, what's up? Yeah. So figuring out the number of peaks we have is going to be the number of proton groups. So we're looking for unique groups of protons. So if I scroll back up here, and I'm going to do it on one of our starting materials just because there's more room. What I would do first is I would draw out all of your implied hydrogens. So on a methyl, we have 3. This one will have 2. Our oxygen doesn't have one. This carbon already has 4 bonds, so it has no need for a hydrogen. This one has 2. And this one has 3. Then we're looking to see if they're all unique. With this molecule, we don't have any kind of symmetry, like, you know, when we have a ring, if there's symmetry, we can have the across the way protons in the same group. With this one, there's not any symmetry, so actually each of them is going to be a unique group. And that proton group is telling you how many signals you expect to see on your NMR. Does that make sense? Do we have other questions? Yeah. Yes. Yes, this is just for an example. With the one that we already did, there were 5 groups. And so then we see 5 signals. Yeah. Aromatic rings are common. So, yes. Yes. Yeah. I'm recording. So it'll all go up. The likelihood of there being a ring is high. The likelihood of there being a ring is high. So do we feel good about this NMR? Can I move to the next NMR? I'm gonna take the discussion that we're not good. Yeah. Yeah, like I'll upload this document when I'm done. Yeah. Question? Yeah. Yeah. I'll just. can I do it for the next compound? Okay, we'll do that. So we have correctly identified the right spectrum to compound 3. So now we can look at compound 4. Now, I'm going to start the same way, which is identifying those proton signals. So I'm going to start by drawing in all of my protons. And then there's not symmetry here, so we're not seeing any identical signals. All of them are going to be chemically unique. So we'll call this A, B, C, D, and E. After you've identified how many signals you should have, you can then go through and figure out what the intensity of each of them is. The intensity is telling us how many protons are in each signal. So for A, we have 3. For B, we have 2. For C, we have 2. For D, we have 2. And for E, we have 3. After you've done intensity, now we'll do splitting. Multiplicity, splitting, neighbors, there's a lot of words for it. It tells you how many little peaks your big peak breaks up into. And how we determine that is looking at our neighboring carbons. So for A, I look next door and I have 2 neighboring protons. Our neighboring rule is always going to be n plus 1. So we have 2 plus 1 is 3. That means that this should be a triplet. Then we do B. B sees 2 carbons. This one has 0 protons attached to it. But if we look to our left, we have 3. So we would expect that to be a quartet. Next, we have C, and both of its neighbors have 0 protons. So that's just going to be a singlet. D has 1 neighboring carbon that has 3 protons. 3 plus 1 is 4. That's also going to be a quartet. And finally, our last one has 2. So now we can go and look at all of the signals we have here. In this one, we have 2 different signals that are both 2H intensity and have a splitting of a quartet. So that's when we need to lean on our ppm chart, which will be at the end of the exam. I'll pull it up. Okay. So we can go ahead and label our other ones, get them out of the way. We have this 2H singlet is going to be C. And then we have these triplets and these quartets. So with our triplets, we have one that is just 1 carbon away from an oxygen. That's signal E. And then we have one on the other side that is 2 carbons away from an oxygen. If we look at our ppm chart, we can see that when you're closer to an oxygen, you have a higher ppm value. So with our higher ppm value, we're going to pick the signal that's closer to an oxygen. Same with B and C. C is in between 2 oxygens, so it will have a higher number. Sorry. B and D. B is closer to oxygens, so yep, D is closer to oxygens, sorry. Oh. Questions on this one?
What's the oxygen you get the part of that food?
Yes.
Yeah.
Other question, yeah, for just the shifts.
Yeah.
So the closer you are to an oxygen, and we can kind of see it here. Our values that are higher numbers are those that are closer to an oxygen. So if you're just in the carbon range, you're looking at 1. As you get closer to that oxygen, you're gonna get a higher number. What's up? No. Was that a better explanation? Okay. Other questions on this? Do we feel good about NMR? Or at least better about NMR? Can we do it at the end? So, we know this is 4. My next question for y'all. This is the same reaction as we just did the NMR for. Can you do the disconnection analysis for it? And also, can you identify what kind of reaction is this? Do you guys recognize this reaction type? Those are the 3 products. What's up? It will make 2 of the 3, but it will not make, like in one reaction, it will make 2 of the 3. It won't ever make all 3 at once. There's just 2 different ways that you could go about it. Both are gonna make that ethanol, but they'll make only one of the bigger ones. Do we know what reaction this is? Yeah. It is a Claisen. How did you know it was a Claisen? The esters. If you see 2 esters as your starting material, that's a pretty good sign that you are going to have a Claisen reaction. And then having that alcohol as one of the products is like final nail on the coffin. This is definitely a Claisen reaction. Do both. Can I get thumbs up, middle, or down for ready to go through it? Middles, thumbs ups and some middles. I'll give you like 2 more minutes. One for each. Okay, are we ready to start going through it? Yes, okay, great. I'm gonna separate this up by color, because I think that'll make it easier. Apologies to any colorblind people in the audience. We're gonna say compound 3 will be blue, and compound 4 will be red. So, compound 3. What's the first thing we need to do in a Claisen reaction? Like if we were thinking about the mechanism instead of thinking about the disconnection analysis. Deprotonate. So, I'm gonna move this back up to the top. With this one, we're gonna break here. And between these 2 protons, one of them will get kicked off. And the bond we're forming is this one, and eventually the one between the oxygen and the proton for the alcohol. From this, these are all the star molecules that we should get. We're breaking 2 bonds, so we will have 4 new products. And then we form bonds, so we end with really 2 products. For compound 4, we're going to do the same thing, except kind of inverse on the molecules. What do you notice is in common between these 2 molecules? There are 2 molecules that they, well, yeah, 2 molecules that they make in common when we're looking at the star method. What are they? They both make an H star, and what else? that O attached to 2 carbons. So that's why when we draw out the products, we have 3 products. No matter which way you do it, you're gonna end up with this ethanol. But depending on who you deprotonate, you will end up with one of 2 products. What's up? Yeah. Which hydrogen are you talking about? Like we labeled them left to right, A, B, C, D. Take which proton instead? Yes, that would matter. If you protonate A or B, you're gonna end up with 4. If you deprotonate C or D, you're gonna end up with. Other questions about a Claisen reaction? I don't have a question on it, but you should also familiarize yourself with the arrow pushing mechanism.
What?
The arrow pushing mechanism, like the curly arrows.
I mean, yeah.
I would not try to put them together. I would say do the disconnection and do the mechanism.
That's so.
Trying to do them in one would get very confusing very fast. So that is one big question, right? We had NMR, we had disconnection analysis, we had identifying the reaction type. Does that look similar to what you guys have had in other exams? Ooh, yeah. 6, like every other exam. Oh, they're about the same. Yeah. That is a hard number to try to approximate. Yes, yeah. Okay. Are we good to move on to the second question? Can I get thumbs up versus thumbs down on how this whole question went as a whole? Great, okay. Question 2. Our old friend PKA. Oh, yeah. So, again, this is a multi-part question. You have identifying the acidic proton, estimating the pKa, ranking them in order of acidity, showing resonance to prove your point with pKa, drawing the conjugate base, and then we even have a little bit of a thermodynamically favorable question. I'm gonna pop the pKa table up on our left screen here. And in the meantime, you guys can start identifying acidic protons. The exact structure would not be repeated. This is just practice. There is only one this super acidic proton. Because it's directly attached to that alkyne. Because if we put in our C's, we have one here and one here. Yeah. What's up?
Oh, that was just like
Lecture 4, the audience says. At the very end. You could also just take a picture of this screen and then it's easy to find. Lecture 5. Okay. Are we ready to start identifying some acidic protons? Ready? Need more time? Not ready. Great. Who wants to volunteer on labeling, highlighting an acidic proton? Come on down. You can do all or none or somewhere in between. I've got it to the highlight right now. Correct. 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 Yes. We have a winner. Buy a lottery ticket. So these are our acidic protons. I'm going to go ahead and draw in these ones that are implied. Did everyone get the same answer? Are there ones we disagree with? What's up? I'm going to hold off on answering your question only because I think it will be easier to answer when we're going through D. Yeah. Yes. Hydrogen innately means, or a proton innately means hydrogen. I understand where you're coming from because a negative usually means a lone pair, but a positive doesn't mean a lone pair, or doesn't mean a proton. A positive means a lack of a lone pair. Yes, we can go through that one. So the fourth one is an alkyne. That's ALKYNE. And I think a lot of people got tripped up on this question when it was on an exam because it's drawn as a straight line instead of how we normally see stuff drawn like this. But those two drawings are the same thing. What's up? Let me pull up my answers. Yes, it is 26. Yes. 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 For my person in the chat, I hope that helped. So estimating pK, we already found out that this one is 26. Can anybody tell me what the pK of the, you have one? What is it? You want to come up here or just tell? I agree. I agree with all of those. Do we have questions on how she found those? We feel good? Question in the back? So, how did she get those?
Yeah.
Let me pull our PKA table back up. Okay, so on here, can you see my laser okay? Okay, great. So with this HBr, if we come over here, we have hydrochloric acid is -7. Hydrobromic acid is -8. This one we look out, it's right there. So then our next one is a protonated ether. So here we see protonated ether. That's basically just when you have an ether group, which is an oxygen in the middle of a carbon chain. If that has a proton on it, giving that oxygen a positive charge, that's a protonated ether, no matter how many carbons are attached on either side of that. And so that's how we know that it matches this one. Even though ours has 2 carbons on one side and 1 carbon on the other, it doesn't change that this is still an ether. So although it doesn't look exactly the same as this one, it's close enough that we'll use that for our approximation. For our next one, we have this amine, which is here on our list, where when we take away a proton, we're going to have a negative charge. So that's here. Following? Yes, no, maybe so? Amine, yeah, A-M-I-N-E. So then our last one, which was heavily missed on the exam it was on, because sometimes this straight line can get people tripped up, but this straight line can be drawn this way. They mean the same thing, where you have 3 carbons, and that terminal alkyne has just 1 proton left. So then if we look at our pKa table, we see alkanes here. We see, there should be alkenes somewhere. But here we have alkynes. And that Y means 3 bonds, like a carbon triple bonded to another carbon. Alkane with an A is a carbon-carbon single bond. And alkene with an E is when it's a carbon-carbon double bond. And then the very last one we have is called a diketone. So when we have just 1 oxygen double bonded in the middle of a carbon chain, that's a ketone. But in this case, we have 2 that are directly, like they have 1 carbon in between them. And that's a diketone. And we can see that structure up here with that 1,3 diketone. Following? Yes? Okay. Other questions on how we got pKa? Yeah. Yes. Other questions? Yeah. Lecture 5 is where somebody said earlier. You will be given this on the exam. You'll be given the pKa chart, amino acid table, and the NMR chart. How do we feel about ranking these? What is our least acidic? 36. I'm going to give these all letters. A, B, C, D, E, C, is our least acidic. What's our next acidic? Our alkyne. Next up, E. Next, B. And finally, our most acidic is A. So something that has an effect on our pKa is resonance. Resonance is the delocalization of electrons. The only structure that we have here that can have some resonance structures worthwhile is this diketone. When we're doing resonance structures of acidic protons, we're going to look at the conjugate base. So what does the conjugate base for this look like? We have our normal diketone, but we would have lost a proton there. Now we can do resonance structures with this. I can push those electrons up onto the oxygen. And I get this structure. I can then push them down and eventually onto the other oxygen. Now, to circle back to your question about how we knew the acidic proton was the one in the middle. Let's say we did take off the proton at the end. We would have this structure. And if we wanted to do resonance with it, this is the, oh, let me add that other digit. This is the only structure we would get. And so because we get more resonance when we do the other proton, that's how we know that that's the proton. Everyone following so far? Feel good about this? Drawing conjugate bases. Anyone? Yes, question first, yeah. Yes. The conjugate base is just after you've removed the acidic proton. It would. Mhm. If you take the proton away, you leave its electrons. Mhm. So, yes, it already had a lone pair to start with, and you gave it a second lone pair. That's why it gets a negative charge. Okay. Good. You want to do the alkyne? Mm-hmm. Yep. very close. You lost a carbon along the way. Oh, yeah. Because if we look here, we have 1, 2, 3 carbons. You only have 2 here. We need 1, 2, 3 carbons. Okay. Everyone agree with my conjugate bases? Do we have questions on how we got there? What's up?
Would any resonant form for the diketone count?
Yes. Yeah. So with the R alkyne. This is our original structure, right? That's what's written on the exam. To help make it more clear, we can draw it like this, where we indicated that this is the acidic proton. So if we lose that proton, everything else will remain the same, except we don't have that proton. And in order to accommodate for the loss of that proton, we would then also have a negative charge there. What's that? Yes. Any of them will get credit. Yeah. Great. Glad we could ask the same question 3 times. Yes, yeah. What's up? Yeah. So this is our original structure. We then lose a proton. So we're gonna have something take that away. These electrons are gonna go back onto the nitrogen. So we end up with 1 hydrogen still there. But now we have an excess of electrons that gives us a negative charge on the nitrogen. Yeah. You don't have to draw the lone pairs. It helps with bookkeeping to make sure that you're on the right track with your charges, but if you can do it without them, do it without them. Other questions? Can I move on? Thumbs up or down? Great. Final part of this question. Using pKa, indicate the direction of this reaction. So what would our first step here be? Write the pKa's. Luckily, you already did that. Now that we have the pKa's, what direction should our arrow go? Oh, question? Yes, question. You guys are facing opposite. Yes. So what does it point away from and what does it point towards? Away from the stronger acid. So we want to point away from the stronger acid. Our stronger acid, which means our lower pKa, means that it is more readily available for losing that proton. It would take a lot of energy to rip off the proton from that amine. But hydrochloric acid, oftentimes in solution, will just exist as its ions. So we are more likely to see that Br minus, or that proton is now on the amine, than keeping the HBr together. Do we understand that? Main thing is you are pointing towards the higher number. pKa wise. And your pKa should always fall under your protonated version. Overall, on the pKa question, that's like our biggest throwback for this exam and this lecture. Do we feel okay about old content like that? Up, middle, down? Middles, ups? Okay, cool. Our next question is very open-ended. I am looking for an example of 4 of the reactions that we know. They can be any starting material, any product, as long as it shows this reaction. So you'll have 4 reactions drawn under this question. You don't have to draw the mechanism, you just have to give me an example for each of these 4 that I have up here.
Would be those 4 tomorrow.
I cannot answer that question. I cannot answer that question. Yes, off the top of the head. What's up? You don't have to, well, you should name the reaction so I know which one you're talking about for which one. Or like which reaction goes to which name. But yeah, you would only need to draw something like this where it's like starting material to product, not anything like your disconnection analysis or a mechanism. I'm just looking for an example that shows that reaction.
So when you draw this out, you need to draw like the arrows and stuff too.
You should have one big arrow that says starting material to product, but you don't need to do like intermediates. No. I am just looking to know that you can come up with and identify a reaction of each of these types. Anybody have one that they want to share with the class? I really appreciate you volunteering so much. If anyone else would like to though, I would love to have more participation. We've got a violent head shake now in the back, so give you the iPad pencil. Missing a bond, but other than that, you're right. And you're right. You have 1, 2, 3. Oh, you don't have to do the intermediate. You can just draw the product.
Oh,
Yes.
okay.
Erase it for clarity.
Oh.
We can also just do this. Put you back to the ring. Oh, then then you can do the full thing. Yes. this is a great example of electrophilic aromatic substitution. We have our electrophile. We have our aromatic ring. And we have that ring substituted. You could have different answers to this. You could use any electrophile, any aromatic ring. This is a very easy one to memorize if you were to do that. Do I have someone who wants to do another one of the reactions? Yes,
But then what happens?
a new contender.
Oh.
Yeah, you don't need to do the intermediate like that. If it helps you in memorizing it to have the intermediate, you can write it, but you don't. No. That's just to help make it clearer to y'all. To label them as an electrophile and aromatic. We have a winner. We have a correct elimination reaction. So, elimination reaction. That's when you, what did we do here? Make a double bond. Do we have a volunteer for acyl substitution or imine formation? Are you doing acyl substitution? Ah, I thought imine would get left for me to do. Good. That'll be helpful. You can just scroll down. Oh, I did not leave enough space. Is that enough space for you? Okay, good. Nope. If you're looking for somewhere that has pretty easy examples of the reactions that you could try to just brute memorize, might I point you in the direction of the crash course document that is already on campus and has been on campus for like 6 weeks. Yes. Questions on imine formation. This is our most recent reaction. And the important parts to remember is that you're taking an acyl of some kind, an amine of some kind, and you will make water and your imine. There's a lot of what up. It can be any acyl. No, it can't be any acyl. It can be an aldehyde or a ketone. Once you start getting into like esters and thioesters and amides, you're going to end up doing an acyl substitution. So stick to aldehydes or ketones. Question?
Well, this has to be allowed to write on.
Yeah. I don't see why not. Question? I would say follow the highlighting. Okay, do we have someone who wants to do an if substitution? Come on. Might give you more space to move it. We already did one. Questions on a substitution? Yes. So with an ACE substitution, we're gonna start with something that kind of resembles an ester. So either an ester, an amide, a thioester, because that leaving group should be somewhat nucleophilic so that it can survive on its own as an intermediate. And so really, we would even see not OH, O minus, but OH. No, no, no. It'll be the nucleophilic side. Question in the back, yes. X minus, she did some of the mechanism. You would not have to draw that part to get credit, but that would be the base that does the deprotonation that starts the whole thing. But you don't need to have that. I can erase it if we need it gone. Questions, comments, concerns? How do we feel about this question? If you were to see something like this on the exam, you would rock it, right? Moving on. So, next question. Draw a molecule with an aromatic ring, 3 chiral centers, an amine, an ether, a diphosphate, a carboxylate, an aldehyde, and a thiol. There are so many correct answers to this question. As long as you draw something that chemically makes sense, like you don't have any carbons that have 5 bonds, and you check all of these boxes, you should get full credit for this question. So if you need like 15 points on the final to pass this class, you could get like 30 just by doing this question right. Question, yeah. Even. Just making an angle doesn't make it a chiral center. Okay,
Oh, okay.
you. If it was in a ring, that might have been why you lost points. Yeah. Question, yeah, what's up? Yeah, sure. So. Where I would start with this is you need some kind of home base. You need a starting thing for this whole molecule. If there's a ring specified in the question, that's a really good place to start. It gives you a whole bunch of options to jump off of to make the rest of your functional groups. So in this question, we need an aromatic ring. I'm going to go with my favorite aromatic ring, the most basic, a benzene. We can check that off. We have an aromatic ring. I'm going to leave the chiral centers to the end, and I'm going to start plugging in different functional groups. So I can start with an ether. And then why don't I keep going with that and do our phosphate groups? So that's ether done, diphosphate done. Why don't I add my aldehyde next? Actually, let me put one spacer in between. That's a pretty long chain, so I'll stop there and keep working on another part of my ring. So I got an aldehyde in there. I need an amine and a carboxylate. Carboxylate is just the deprotonated version of a carboxylic acid. So I'll add that over here. Done. Then I need an amine and a thiol. I also need to remember to do those 3 chiral centers. So if I add a thiol here, that turns this into a chiral center, because now I have 4 unique substituents. I have the ether, the diphosphate, and the thiol, plus that implied hydrogen that I now made explicit. So I've got one of my 3 chiral centers. And I finished out my thiol. I'll put my amine here, and we'll just do proton here, but I'm gonna make it a secondary amine. So I'm gonna have another carbon chain come off here. With that, I need some more chiral centers. So I'm gonna make sure that all 4 substituents are unique. I'm gonna do that with this one too. Done. What's up? If they are actually chiral, yes. Like that. That is not chiral. No. Because, yes, because that only has 3 substituents. Then yes. But you need an aromatic ring, so you would need to have another ring, yes. I would say the easiest way to get your chiral centers is to throw some halogens on there. One, yeah, that is an easy way to make sure that all 4 of your substituents are different. Because you have 1 chlorine, 1 bromine, 1 iodine, 1 hydrogen, That is 4 different constituents that you can pull from. What's up? Yes. That was something people lost points on last exam, which I'm going to do now, because the graders have a lot of grading to do. There are 200 of you in this class. And you finish the exam at 3 p.m. on Friday, and they are supposed to have it done graded by 8 a.m. on Tuesday. So label it so they can grade it faster. To my question in the chat, what is the CH2? It is just a linker to link things together. It has no real importance. No. Again, I'm gonna default to, you should pay attention to things that are highlighted. He asked what, functional groups are like really important to know for the exam. And I said, highlighted things usually have importance. Yes. It is. The structures, no. You do not need to know. Okay, how did we feel on this one? If you guys have felt good about all of the questions so far, you are 2/3 of the way through the exam. Okay. Next question. I have a reaction up here. It is a decarboxylase reaction. Decarboxylase, like the enzyme. It needs a cofactor to do its chemistry. What cofactor does it need? Anybody have any guesses? Any thoughts? You know. Yeah. You're gonna do great. Yes. For our purposes, yes. It's me being lazy to draw benzene. No. It's a way of saying resonance between the whole ring. What's up? You would use TPP for this one. Can you tell me how you knew it was TPP? Yes, that's exactly right. So it's TPP. Some of the other cofactors we know are PLP, which also does decarboxylation. But as my friend here pointed out, TPP works on alpha keto acids. For those of you who don't know what an alpha keto acid is, it's where you have 3 of those oxygens all close together like that. Whereas PLP is going to work when there's a nitrogen close by. What are some other cofactors that we've learned about in this class? Yeah. NADH, NAD+, coenzyme A. None, I guess, also works. Moving on. Questions, comments, concerns. Yeah. A good way to study those is at the very end of the crash course document. I have a list of the cofactors and what kind of reactions. What's up? For the sake of time, no. For the sake of time and prioritizing what you need to know for tomorrow, no. Okay, question, yeah. Cofactors were very recent. I'm gonna say in the last 4 lectures. Other questions, comments, concerns?
To recognize the reaction, right, which
Can I move to the next part of this question? Thumbs up, middle down, up, good, great. Identify secondary structure motifs on this nifty little picture I have here. What are the 3 structural motifs that we should know? Hey,
Alpha helix, beta sheet.
so true. Do you know which are on here?
Yeah.
Do you want to tell me or come up here? You can
I can
do
check it out.
I would love that.
The red one is gonna be the alpha helix. The green are the loops. And then the yellow pieces are beta sheets.
Now, you are correct. What would you do if this was printed in black and white? Because A&M has no money and no money for printing colored exams.
The beta sheets are flat.
Beta sheets are flat.
Loops are skinny
Yeah.
and the alpha helixes are like fours.
Yeah.
Or helixes, like that.
Sort of. They like kind of thought about that when they were naming it. Just like
I wouldn't imagine
a little bit. Questions on this? This was like almost an exact question from y'all's homework last time. I did not say that. You didn't hear me say that. Definitely didn't say that. If they had money, they'd pay grad students more, right? Anyways. Okay. Next part. Draw the sequence, what do I mean by that? No. Yeah. So amino acids, they have these nifty little 1-letter codes. I'm about to put them up on the screen for y'all. So we have all of these amino acids. I have given you a sequence of amino acids to draw. Draw it. Like it's so simple. I'm kidding. I know that it sounds simple to you guys. How do you feel going into this question? This is like very new content. It was on a homework. Anything on a homework is free game, y'all. What's up? You can. I don't approach it that way, but if it's easier for you to approach it that way, then yes. Yes, it will always be the same. That's the whole motif behind like protein structure. It will always have an NH2 on one end and a carboxy on the other end, unless explicitly specified.
Maybe she just looked.
So can I get thumbs up, middle down about how we feel about a question like this? Okay, lots of downs. Oh, come on up. You want to? Okay, so instead of having somebody work through this or giving y'all time, I'll just go through it step by step so that y'all know what to look for. So the first thing that I would do when you get something like this, you can write on the exam. Go ahead and circle the amino acids that you're going to use so you can keep an eye on them. So T is our first one. If I can find it up here. Green. That's our starting one. We can circle that one. Our next is histidine. It's down here at the bottom. And then E is a glutamic acid, which is over here. The thing about amino acids is that they form all of the proteins in our body. How they do that is they make this chain that we can see in this picture that eventually folds up and looks all funky. But the backbone of all amino acid sequences is the same. It's the same. So I'm gonna put this away so that I can keep an eye on my other things. The first thing I'm going to do is draw out that backbone. We are always going to start with the amine side. And the pattern to remember is carbon, acyl, amine. We have 3 amino acids, so we're going to do this 3 times. Amine, carbon, acyl, amine. We have 1 more. Amine, carbon, acyl. Actually, let me draw it the other way so it looks the same. Amine, carbon, acyl. We end with the acyl. And that's where we see it as a carboxylic acid. Each of these blank carbons that are left, they get the R group from whatever makes this amino acid unique. So for T, which is threonine, this is our R group. And we get that from looking at the table. Yes. So threonine. Okay. So this is the amine, this is the carbon, and this is the acyl. This group here is that R group that we add on. So for our next one, we're looking at histidine. Histidine is down here. We have our amine, our carbon, and our acyl. So we're going to add this group onto our empty carbon. Following? Yes, no, maybe so. Our last one is glutamic acid. We have the amine, the carbon, and the acyl. Because we don't have another amino acid hooking onto this, that acyl group remains as a carboxylic acid. And we're going to add on this carbon chain. When you're hooking together amino acids, you're making peptide bonds. Peptide bonds we recognize as amide bonds. So really what's happening is acyl substitution, where we have these carboxylic acids that are going to do an acyl substitution with the amine from the next one. And that's how they keep hooking together until you get this long beaded chain of amino acids. But each bead has a unique R group. And as those start interacting with each other, that's when we start getting protein. For our purposes, you just need to know how to make a little chain of them. Yeah, question. Because you do an acyl substitution where this amine attacked that carbon site. And so every time you do this, you make water. So I lost a water connecting these two, I lost a water connecting these two. And then the hydroxy stays on because I didn't connect another amino acid there. No, because we lose it when we connect it. Yes, if we connected another one, this OH would be replaced with the amine of the next one. It will always start with NH2 and it will always end with carboxy. Unless explicitly said, so I think in the homework, where did I put the pencil? Oh. In the homework, there was a question like this that then said COOH. That's telling you to have the OH instead of sometimes you can do the O minus. But it will like explicitly say what you would add on the end. Question. Don't worry about that. Proline. Proline is a weird one. Other questions? There was one in the chat. Let me go see. So which amino acid is which? We can actually highlight them. Is that clear enough for my people not here? How would we feel if we saw a question like this on an exam? Okay. We're moving on to my last question of the evening. You would cry? Please don't cry at the exam. I can't scan in what paper. Say it again. Sure. Sure. I'll put that in the rubric. Part of it is, you do not need to memorize this stuff. You will get to see, oh. Sorry, my people on Zoom can't see that I have a third screen up. You will get an amino acid table that has like the full government name of the amino acid as well as, actually, let's see if I can turn my camera on and just show you guys. Okay, maybe I can't show the video. But there is an amino acid chart that you'll get that has the 1-letter code, the 3-letter code, and the. Do we feel okay about protein stuff? Good, thank you. Thank you for responding. So we have reached my final question of the evening. This question should look familiar because you just had a homework question that looked really similar. The first step of this, you do basically no chemistry. I want you guys to be getting full credit on that. It is picture drawing. Please guys. I have a reaction up here. We have starting material and products, but I've left some details ambiguous. We have 4 R groups, and I've given you some substituents. You can plug them in wherever you wish. You will use each one once. It is important where you put them because their location changes with your product. Question. This has not been on any of the exams. There was a question like this on a homework. That is the full reaction. Just remember they could do that. Okay. Anybody recognize this reaction? What's going on here? It is. What kind of aldol? Is it just an addition or is it so true? It is in fact an aldol condensation. How did you know it was an aldol condensation? So true. H2O, carbon-carbon bond. And the two esters. Okay. I'm gonna take this down. Anybody feel confident about their matching game? No. It does not matter. As long as you use each one once. You just gotta. Yeah. The mechanism does come up later, but for this part, doesn't matter. Anybody? Viewer? Okay. Then I'll do it. So our first substituent that we have from our bank of substituents is this 5-membered ring. I'm gonna use it as R1. I'm gonna use the triangle as R2. Bam. I already got half of this down. We have 2 left. R3 is just 3 carbons. And R4 is an aromatic ring. This part is where it gets a touch complicated because we have to think about where our reactants will start and where they end up. Ta-da! Questions on how this happened? All I did was replace an R with one of the structures that were given. Yeah. Nope. Yes. Nope. Nope. For this question. We will. But for now, all you had to do was that. What's up? Because I have it drawn wrong up here. Oh. It's drawn right below it. I don't know why I drew it right for the disconnection analysis and wrong for the other one. Human error. What's up?
If this were to be on the exam, would the product have like, would it be matching exactly like that? Or like, would it be like R5, R6, R7, and then you would have to know how it?
It would be like on the homework where it's
Okay.
5, 6, 7. So. Gonna move on to disconnection analysis, unless there's questions on this one. Can I get thumbs up, thumbs middle, thumbs down? Ups, great, moving on. So we know this is an aldol condensation. No, no. I drew it again because it'll be easier to do with the R's. Because you guys might not have picked the same R groups I did. And that's okay, it's still correct. But I'm gonna do the very general answer. Try to do the shapes. If you are getting lost with the shapes, do the R's, because that can at least get you partial credit. I just don't know yet if it's gonna be partial or full credit for just R's. So, disconnection analysis. I'm gonna need to draw in some hydrogens. Do we all agree with my disconnection analysis? Yes, no, maybe so. Can I get thumbs up, thumbs down, some kind of alive out there? Okay, cool, thank you. Can we do the curly arrow mechanism for this? Do we feel confident on that? Yes, no, maybe so. We'll work through it. So. What do we need for an aldol condensation that I have not written up here? A base, exactly right. So. We need a base, and it is first going to D-propane. Now we have our H base floating around, and we can bring in our R3 and 4. I made a nucleophile. It is going to attack our acyl center and push electrons up onto the oxygen. Yes. Oh, I forgot the O. So true. There should be 2 H's and 1 O. So I still have this H base floating around, and when I made my tetrahedral intermediate, Where we differ between aldol condensation and aldol addition is that we are now going to not break down our tetrahedral intermediate, but rather we're gonna make a hydroxy. So it's gonna attack that proton and the electrons will go back to the base. So we still have one proton hanging around here. It was always here, but I stopped drawing it because it wasn't participating. But it's about to participate. So we'll attack, the base will attack the proton and put those electrons back onto the oxygen. Now, we're gonna form our double bond. So we have H base hanging about. And this anion is gonna come here and kick off the hydroxy. And that hydroxy is the starting material for our water. Oh, I am all over the place with this drawing. This is also wrong. R4. Our final step is we're going to complete our water and also restore our base. And that is the mechanism for our aldol condensation. Questions? Comments, concerns? Yes. If it was an aldol condensation, yes. What's up? Yeah.
One question for you. Is asking us to draw clearly that we react. Something we're gonna have to.
That's okay. Other questions? This is the last, bless you. This is the last question I have for y'all. So, yeah, what's up?
Hey, go back to the
Can I go back to what? This one?
no, for like this.
Oh, sorry. Here? Do you have a question on it, or you just wanted to see it again? What's that? Yeah. I didn't, but I am breaking it twice. I would say that that's fine. Okay. Question in the chat was, do we have to do all these structures on the exam? For a mechanism, yes, you need to draw all of the intermediates. That's a huge part of curly arrow mechanisms, is you have to be able to show these intermediates. What's up? Yeah, he's just hanging out. How do you do the chemistry if you don't draw the base? Like this one? No, that's okay. For R1 or R2, I would say try to draw the structure, but if you're getting lost trying to include all of the different R groups, it is better to just do the R groups and take the partial credit than to like do incorrect chemistry of drawing out the structures. You will get a majority of the points if you have correct chemistry, and the only difference is that you put R's instead of the actual structures. Other questions? If not, that is all I have officially prepared for you. I'm willing to take other questions if you have other concepts that you're. Thank you for announcing them because I cannot see you behind there. Yes, yeah. Yeah. The problem with that is I don't have an NMR prepared for it. Yeah, so I can just draw like a really general ring and we can talk about it. So if you have a ring like this, that has stuff coming off both sides like that, across from each other will be proton groups. And that's because this carbon is 1, 2 away from a nitrogen and 1, 2, 3 away from an oxygen. Yes. Well, because it's symmetrical, they look the same. So you only look at one and it will be the same. But you have to remember that for intensity, you'll count the protons on both sides. But splitting will only look at 1/2 of that. Question, what's up? No.
Any specific topics at all?
This stuff. Yes.
Just that part thing you're doing, you only work if they're up to the branches are on other sides of the.
Yes. If they were like this, that is not the same, and they will not be symmetrical. What's up?
Again, I'll probably. Both are reactions. Both of them. You know, are we gonna have another structure?
You do not need to have cofactor structures memorized, no. Other questions? Yeah.
There are none.
Could you expand on your question? Yeah. So yes, that one is resonance. So we kind of worked it out here. Where if we were to take off that proton, we only have one other resonance form.
I mean,
Whereas if we take off the middle one, we have 3 resonance forms. More resonance means more stable, means more like okay with that proton leaving, and that makes it more acidic. Other questions? Well, I'll probably never see you guys again, so have great lives. I don't proctor your exam, so you have a question. I will stick around if people have other questions, but for the most part, this is where the big session ends. Bye forever. Hope you have great lives. You've been excellent students.
No, I think we can study this.
Yeah. I'm gonna shut this down. Yeah.